Okay, so in this video let's consider an example for a conservative system. Say a particle with a mass m is equal to 1, some unit, okay, and that particle is in a potential field which is given by this equation. Okay, so now we could see that it's a there isn't any damping or anything, so we can ignore that. Then for this system, what is the phase portrait? So that's what we need to identify. So the first thing is we need to identify the equilibrium point, and then we need to construct the phase portrait, and then we will try to understand what is the meaning from the phase portrait. Okay, so now the potential energy has been given. So this form is known as double well potential. Okay, and from this the force, which is equal to x minus x cube. Okay, so that's the force which is acting on the particle, and the force is going to vary as the position of that particle varies. Okay, and the equation F is equal to ma. From that we will get this one. Since m is equal to 1, we have only x double dot. Okay, now we know how to write this equation, the second order equation, into two first order equation, and if we do that, we will get this form where x represents the position and y represents the velocity. Okay, now what are the fixed points? So the fixed point, identifying the fixed point is easy. The point where y is equal to 0, and other points like the y dot will go to 0 when x is equal to 0 or x is equal to plus or minus 1. Okay, and from that we could identify these three are the fixed points. Okay, now what kind of fixed point is this? Let's try to use our linearization and identify the Jacobian matrix, and let's try to classify the fixed point. Okay, if we do, what we will get is this fixed point is a saddle point. Okay, fine. How about these fixed points? These fixed points gives tau is equal to 0 and delta is equal to 2, which means it's telling it's a center. Okay, if it's a center, we cannot be sure whether it's exactly center, because it's a borderline case, so it could either go to what to say, unstable spiral or stable spiral, or it could remain in center. So we cannot say just by doing the linearization, right? However, if it's a conservative system, we can say that. Okay, so that's the interesting fact about the conservative system. Okay, now from the physics, okay, we could say that the energy will be conserved. Okay, so this is the potential energy, and we know what will be the kinetic energy, and from that what we could identify is what is the total energy, and the total energy is given in this form. Okay, so in the place of x dot square, we could substitute this one. Okay, so okay, if you see this part, the second part, okay, or minus 1 by 2 x square plus 1 by 4 x to the power of 4, that comes from the potential energy, and the kinetic energy, which is half mv square, where m is 1, v square, which is x dot square, which is y square. So therefore we have this term. Okay, and this whole thing is conserved, okay, for this system. Okay, fine. And our claim is for such a system we cannot have stable spiral or unstable spiral. Okay, it will be a we can expect center. Okay, so from this E, how can I construct the phase portrait? Okay, so if you use a numerical method, then you will obtain the phase portrait like this, but we are going to just use this equation and we are going to construct this phase portrait. So how are we going to do that? What we are going to do that is in the place, so this is going to be constant, and the constant depends on the initial condition, right? So for an initial condition, E is going to take some value and that is going to be remain along that trajectory, right? So for some particular constant, okay, this equation will provide a contour, right, and that contour represents a trajectory. Okay, so in order to construct the phase portrait, all I have to do is choose different constant and construct the contour. Thus we will get this phase portrait. Okay, so it's as simple as that. So that's how we can construct the phase portrait for conservative system. Okay, so let's try to understand what does this mean. It means if I start somewhere here, okay, I'll be circling like this. If I start somewhere here, then I'll be circling like this. If I start somewhere here, okay, what will happen is I'll be going like this, and then I will not just circling this one, I'll be going further and I'll be circling this one. Okay, I'll be circling like this, and not exactly circling, but it'll be a periodic oscillation. Okay, and this particular trajectory is an interesting thing. So this particular trajectory is known as homoclinic orbits. Okay, so what does this mean? It means it will start at some fixed point and then it will end at the same fixed point. Okay, but the other trajectories are the other closed orbits. Okay, it will start and end at that point within a finite amount of time, but this one trajectory will take to complete its orbit, okay, infinite amount of time. Okay, so that's one thing we need to remember. Otherwise, for other trajectories, it has a finite time period. Okay, even for this or for this, every other things. Okay, so so now we know how to construct a phase trajectory, and we could understand how the system behaves based on the phase portrait. Okay, so in this example, what we are going to do is how can I understand the phase portrait just by using this equation. So in order to do that, what we are going to do is we are going to plot this function e of xy, okay, by considering x and y in one plane, and in the place of e, so I will consider that z. Okay, each z value represents one of the e value. Okay, so first I will do the plot. Okay, and that plot, in that plot, a particular height or the particular z value represents when I section this energy surface or energy function with the z is equal to something plane, then those two things will intersect, and that intersection will provide us a trajectory. So the projection of that particular intersection along this xy plane will provide us the that particular trajectory. Okay, that trajectory corresponding to that E value. Okay, for example, for this particular E value, we are actually having two trajectories. One is this one and another one is this one. Okay, so that's how we could construct the phase portrait. So there are some online tools which are available to construct the 3D surface. Okay, so just look at this one, and you could use this. And here I have, in the place of E, so this is E actually, and I have written the equation. Okay, and then I have plotted within this range of x and within this range of y. Okay, and this is the energy function or energy surface. Okay, so now if you see that okay, this blue color represents how deep it is. Okay, and or how bottom it is, and the red one represents how large the z value is. Okay, this represents how small the z value is. Okay, now from this picture we could see that here there is a lower point, and here is another lower point, and if we let's say if we section it somewhere here, okay, then it will be orbiting over here. Okay, similarly, if the initial condition is over here, then it will be orbiting along this closed orbit. At the same time, if it's somewhere here, then it will be orbiting like this. Okay, so what you could do is you could use different energy functions, and you could plot, and you could try to understand the phase portrait for different conservative system. Okay, so in the next video we will see about some other classification of nonlinear systems. Okay, thank you.